So good afternoon and welcome to the Mechanical Engineering webinar. Today we are here with Professor Jim Duncan, who is the head of the Division of Thermal Fluids and Energy Systems here at the University of Maryland. And my name is Megan Petrie. I'm the Graduate Program Coordinator for Mechanical Engineering. So today we're going to talk a little bit about the division and answer any questions you have about the program. So I'll let you begin.
Thank you, Megan. I'm a professor in the thermal fluid sciences area, and I work in fluid mechanics myself, but as the head of division, I thought I would talk about the various things that are done with our group of faculty in terms of research. This now?
Spacebar.
Spacebar. Oh. No. A little bit of technical difficulties here.
There you go.
Which one now?
The spacebar.
Still the spacebar. So here I've listed a number of research areas that are covered by the faculty here, starting with hydrodynamics and turbulence and biological flows, mostly fluid mechanics in the top group, and then getting into the energy sciences, heat transfer, air conditioning and heating, fuel cells, etc., down below. There are four centers and programs involved in this area. First of all, there's the Center for Environmental Energy Engineering, and then the Berger's Program for Fluid Dynamics. I'm the chairman of that now, or almost the chairman of that now. And the University of Maryland Energy Research Center, UMERC, and the Maryland Nano Center. We have faculty either heading or involved in all of those areas. And here I put a list of all the faculty and research areas that they cover. There's 14 of us, though, so reading through them is a little boring, but you can see them here. And I really advise you to go to the department's website and look at the list of faculty and click on various people, and there you can see anytime you want the research areas of the group of us. And here is the second half. Whoops, the second half. With Johan Larsson up on the top, one of our new assistant professors, or old assistant professors, and Siddartha, also a new person here. So I thought what I would do is just highlight the research areas of a few people. And the first one I picked was Amir Riyadh. He does computational fluid dynamics work, and one of his areas of expertise is in flow and porous media. And I'm sure you know that one of the ideas in reducing the CO2 emissions is to capture CO2 from power plants, etc., and then pressurize it and put it underground. And if you're doing that, one of the problems you have is that you want to keep it there for thousands of years. And it is a fluid mechanics problem. You put in the compressed CO2, which I think is heavier than the brine that's already in the rock. And, you know, these reservoirs are really kind of cracked rock. And it's not just an empty space down there. So this porous media flow is appropriate for that, and it's a multi-phase system with CO2 and brine. So in this simulation that's shown over here on the right, the top is an initial layer of CO2 and the bottom is brine. And when the movie plays, I hope you'll be able to see it. No. How do I go back, John? Try it again. Well, it's a cool little simulation, but for some reason isn't working. Well, what you would be seeing is fingering, like you see here on the left, where the heavier stuff goes down into the flow below. And this simulation is in hours, but in reality it would be years and years over which this occurs. So you're trying to predict what will happen to the CO2 over the long term. Another one of our professors, Yelena Freiburg, is working on sustainability in the built environment. It's one of the NAE's grand challenges in engineering. If you look at energy consumption in the planet, and particularly in the United States, you'll find there's a large portion of it that goes into heating and air conditioning buildings. And she's working on one of the ways of minimizing the energy costs of this, and that is to start, instead of just heating the whole floor or the whole building to a certain temperature, to monitor the occupants and see when they're comfortable and when they're not, to look at their skin temperature and try and have locally controlled heating and air conditioning so that you can reduce that. And shown here on the slide is some of the data that they took. On the left you can see this person here with the skin temperature done in color, I believe, and these are just a flow chart of how you might do it. And they were able to get, a significant reduction in the energy cost for a building on the order of 20% by local control according to the needs of the people in those spaces. Johan Larsson is working on a multi-physics turbulence approach. Here, he's a computational fluid dynamics person, and here he's shown a scramjet. And the idea of a scramjet is that they work at supersonic speed with essentially no moving parts. But through combustion and control of the shock waves, et cetera, they're able to create thrust and power the vehicle. It's a very new it's not a new concept, but it has never really worked completely well yet, and there's still quite a bit of research that's done on that. So this is all done computationally by Johan and his students and postdocs. As I mentioned, Siddartha is one of our new faculty members. He works in fluid mechanics as well, and he works on the other end of the scale for very, very tiny systems. In biomedical research and in 3D printing, etc., people start working with very, very, very tiny little droplets of fluids. In some cases, how they respond to sitting on surfaces, which is shown up here on the right, with a droplet sitting on a soft surface, which might be a layer of chemicals or drugs, and trying to understand how to manipulate them and what will happen when they're sitting on the surface. And over here, he's showing this evaporation-triggered nanocomposite formation. The idea is that when the evaporation occurs, you get this distribution of little tiny drops, and when that all dries out, you're making a material out of it, and you'd like to control the distribution of droplets, etc. And so that's a very hot area of research at the present time. Jeongho Ken has been working in boiling heat transfer for some time. He works in other areas too, but I chose this one because of the little movie, which we probably can't see. I guess not. One of the problems that he's worked on is the idea of boiling in space. So if you're on the International Space Station or in some application where for a short time you're at zero gravity up in the air above the Earth, then your boiling characteristics change. If you go in the kitchen and you boil a pot of water, you can see the bubbles coming off the bottom, and they rise because of buoyancy. But if there were no gravity, they might not rise. They might stay on the surface, and that will dramatically change how the boiling occurs. So he's had experiments up on the space station and also on what's called the Vomit Comet, which is a fun movie if you can see it. An airplane, this is the interior of the plane shown over here on the right. It goes up to a high altitude and then flies in a parabolic trajectory downward. And while it's in that trajectory, there's almost zero gravity inside the plane, and people go flying around, and most of them get sick. So that's the name. And I added one of my own, but unfortunately I can't play the movie, so we'll never know. But I'll go backwards again. That's over here. It's an experiment on droplet production by breaking waves. It's an important phenomenon because it dramatically affects the transfer of heat, mass, and energy between the ocean and the atmosphere, and therefore affects weather systems and climate. When people make climate models or weather models or storm tracker models, they have to consider this. It's one of the big energy sources for storms, for instance. And so we were doing some research on how breaking waves generate droplets. On the top, you see 6 holographic movies of the droplets coming off the surface. We're able to track droplets down to 50 microns and, as they move above this measurement plane we have. And on the bottom is the profile of the breaking wave. If only you could see it play. Again, I invite you to take a look at our website and see everybody's different research areas. And I hope that my little smattering of research accomplishments was of interest.
You certainly share a lot about what's going on in the department. Is there any kind of innovation or anything that you're most excited about within your division?
Well, I know the fluid mechanics the best, but I tried to pick the ones that I was most excited about to show.
Okay.
Yeah.
And is there anything in particular, specifically when you're interviewing or starting to Skype with students who are applying to the program, that you look for in a student or qualities that you think they should bring to the program? Interest in really getting into research and working hard in an area is very important to me in addition to their academic records. And any other skills that they should, or experiences they should have before coming to grad school?
Well, none are really necessary, but if you're an experimentalist like me, you might notice whether someone has done experimental work or made things before or likes to work with equipment or whatever, because then you have an idea that they kind of know what they're going to get into. It'll be useful. And I know if I were a numerical person or a theoretical person, I'd want to have some evidence that they knew what it was to program and have some experience with that. Those would all be pluses.
Okay.
Yeah, not necessary, but pluses.
Do you think there's one or two attributes at the University of Maryland that really set us apart from other programs?
Yeah, I think that the faculty are really dedicated here. We have a growing program, constantly improving and increasing our status, and I think the people here are very involved, and so it's great to get new students in who want to be equally involved.
I don't see that we have any other questions coming up on the webinar. But anything else that you'd like to add that you think students or applicants should be excited about when looking at mechanical engineering here at Maryland?
Well, I mean, I would make a suggestion instead. I would make the suggestion that they contact faculty. Look on the website, find faculty that you're interested in their research, and send them an email. I mean, it's the best way to do it. It's not as much like undergraduate school where you just kind of apply to a university. Here you're really applying to a faculty member or two. And making contact is really the best way to do it.
And they can just send an email. There's no specific language they need to use or anything specific they need to say. Just send an email. Yeah. Send an email and say, I'm interested in your research. I'm applying to your school, or I'm interested in applying. Do you have a minute to talk about it? And would you recommend they also maybe share a little bit about what they're interested in, or what kinds of research they've already done? Oh, yeah, sure. It's better if you attach your resume to the letter and talk a little bit about yourself, too. Okay, that sounds great. Well, if you don't have any other questions, I would just encourage anyone, if you're interested in the program or have questions for us or Dr. Duncan, just reach out to us. You can email the graduate office at megrad at umd.edu, and we will forward you on to the right person. So thank you for joining us today.